So, in the 1960s, we had a particle zoo. That is where um, people were discovering so many particles that were smaller than atoms, particles from atoms, um, that they called it a zoo. They had, there were hundreds of them. They were being discovered every week. Now, this is because they had created particle accelerators to accelerate um, protons uh, and charged atoms at high speeds, collide, and then measure what came out of those collisions. And lots of things came out of the collisions. So they had this particle zoo. Now, in 1964, I think it is, um, someone came up with a theory that said that all of these particles that they had been discovering were not fundamental. Instead, there was a smaller set of fundamental particles that, when put together, made up the particle zoo. For example, we have over 100 different types of elements, right? But each element, each type of atom is not fundamental. We know that elements are made up of protons, neutrons, electrons. So there's three things that together in different combinations make up 100 different things. Same idea here. We've got 100 different subatomic particles, smaller than atom particles, but just a few things combined are going to make those subatomic particles. Okay, so we had evidence that protons and neutrons are not fundamental particles. Okay, and we had lots of subatomic particles other than protons, neutrons, and electrons. We had hundreds. So in that case, if protons are not fundamental, then what are they made of? Well, a lot of people might tell you that a proton is made up of quarks, particularly two up quarks and a down quark. And up quarks have a charge of positive a third, positive 2/3, and a down quark has a charge of negative 2/3, 1/3. I think I've got this right. So when you add positive 2/3 minus 1/3, you end up with a charge of 1, the charge of one proton. This is what people will tell you. It's not quite, it's correct. The proton does have two up quarks and a down quark in it, but it can also have lots of other types of quarks inside it as well, which are constantly being created, annihilated, turned back into energy, back into mass, back and forth all the time. There's also lots of gluons inside the particle holding it together with a strong nuclear force. There are bosons there are bosons going in between the quarks, changing the color and things like that. So there's lots of particles inside a proton, but each proton, I guess what makes it different to what a neutron is, it's got two ups and a down as well as the other stuff. Neutron has two downs and an up. Two downs, so negative 2/3 plus an up positive 2/3 cancels out, makes a neutral neutron. And it also has the gluons and other quarks in there and antiquarks and stuff. Okay, so protons and neutrons are not fundamental particles, they're made out of quarks. Okay, and quark composition hadrons, that is when you put quarks together to make another particle, such as a proton or a neutron. They are quark composition hadrons. So what are all the fundamental particles then, if they aren't fundamental particles? We have 6 quarks, up, down, strange, charm, top, bottom. Great names. Up, down, strange, charm, top, and bottom. Okay, we have so those are the quarks. We've got the leptons, and some of these might be somewhat familiar to you. We have the electron, the muon, which you might remember from when we were talking about Einstein's theory of relativity. Muon decay is one of the main pieces, or one of the easy to understand pieces of evidence for time dilation. We have the tau, which you probably haven't heard of, and then we have the neutrino, but we have, for each of these three leptons, we have a different type of neutrino. So we've got the electron neutrino, we've got the muon neutrino, and we've got the tau neutrino. Okay, those are our leptons. So the electron is a fundamental particle that we've heard of before, even though protons and neutrons are not. And then we have the bosons, and you would have heard of at least one of these before, the photon And the bosons they are what control forces. So electromagnetism is controlled by photons. Anytime magnets push against each other or a proton and electron attract, that is the photon at work. Then we have the gluon, and the gluon controls a strong nuclear force, literally gluing things together. And then we have bosons, the Z boson and the W boson, and those control the weak nuclear force, which we don't talk about much in this course. And then, okay, so this was the standard model of matter, which is all of the particles and all of the forces. There are definitely some questions about this that we don't know. Yes, the fundamental forces. So there are four fundamental forces. Um, they are the electromagnetic force, controlled by the photon. We've got the strong nuclear force, controlled by the gluon, and the weak nuclear force, controlled by the two bosons. However, however, there's another force, uh, gravity, and we don't actually have a particle that controls gravity. We don't know exactly how it works. So even though it's the first force you learn about, it's the one that physicists actually know the least about, which is interesting. Some people would say that there's a particle called a graviton or something which controls how gravity works. We're really not sure. Okay, so there's the fundamental forces, the leptons, the quarks, these are the forces. Okay, and now we need to investigate the operation role of particle accelerators, and there's one in particular I want to talk about, to test theories such as the standard model of matter. So the one I want to talk about is the Large Hadron Collider. Um, a man named Peter Higgs is a theoretical physicist. He's still alive, and he looked at the standard model. He looked at these particles and fundamental forces, and he did a lot of theorizing to try and come up with a explanation of how objects can have mass. Okay, some of these particles have mass and some don't. The quarks do, the electron does. Um, Neutrinos we think have mass. Seems like they do, but it's very, very tiny. But the bosons do not. The photon has no mass, for example. So why do some particles get to have mass and some don't? And so Peter Higgs said that particles have mass when they interact with a field, which he named the Higgs field. And just like any field, if there's a vibration in that field, that vibration can form a particle, which would be the Higgs particle, or the Higgs boson as it was known. So he used the standard model to come up with a theory, and that theory had a prediction. The prediction was that this particle called the Higgs boson should exist. And then lots of people jumped onto his theory, did a lot of mathematics, and worked out roughly how big the Higgs boson should be, what it should interact with, if it breaks down, what parts does it break into. Okay, so we created a machine. The machine was called the Large Hadron Collider. Large Hadron Collider. And this machine is big. It's a tunnel, a circular tube that's 27 kilometers long. And inside that tube, they accelerate protons very, very, very close to the speed of light. They accelerate them one way, close to the speed of light, and they've got them going the other way, close to the speed of light. And what they do is they collide them. When they collide, bits fly out, and they measure all the bits. And they were trying to find the Higgs boson, and they eventually did find it. And they announced it in 2012 that they had found the Higgs, and it had a size of 120 electron volts or something like that. I don't actually remember the number. But this is remarkable because the Higgs particle was only theorized based on the standard model, right? We only discovered the Higgs because we had this theory. The theory predicted it, we searched for the prediction, and we found it to be true, which is very strong evidence that the standard model is on the right track. There's lots of reasons why the standard model doesn't work. For example, we don't know how gravity works. The standard model also doesn't yet fit in properly with general relativity. So the standard model works well with quantum physics. General relativity is still a separate thing. We're trying to merge them together. And The standard model doesn't account for dark matter or dark energy as well. Um, dark matter being clumps of the universe that have gravity where we don't see anything to have the gravity, and dark energy is whatever is causing the acceleration of the expansion of the universe to accelerate. We don't know why that's happening. So standard model is our best current guess at how physics works at the most fundamental level, but it still has issues. Even though it has issues, it's got some really strong evidence behind it, such as the Large Hadron Collider finding the Higgs boson. That's physics done.